like polio.
It's my pleasure to introduce our team, the Dean from the College of Business, and his associate is interested in his concentration is machine learning. I think this is a very important presentation because so much of what we hear has been in the past. But now we're going to get a look at the future. I'm intrigued by Dennis's getting a machine learning course in before I did. I'm very jealous about that.
I was lucky.
So we're going to hear about these new approaches to medicine and get used to them because they are coming. Thank you very much.
Thank you, John. Good afternoon.
Good afternoon.
Good afternoon. Make sure do a mic check for our colleagues online. Can you hear us? Say something.
Yes. Yes, we can.
Good afternoon.
So good. So whoever is the person, we can send you a free sandwich for. Again, Dr. Sennett, we're truly honored to be with you today. My name is Moez Limayem. I'm the Behnke Dean of the USF MoMA College of Business, and I'm joined by an incredible colleague, probably the best in the world in this area, Dr. Balaji Padmanabhan. He is the director of our Center of Analytics and Creativity, and really just a word authority. We stole him from Wharton 7 years ago, and every morning I check on him to make sure that he's it is really a pleasure to be with you today, and I'm gonna try to share, right? No? Yeah. I share the screen. Yeah. Okay, good. Good. All right. Good. So the topic of the talk, as John mentioned, is machine learning and artificial intelligence in healthcare. Last night we had an incredible dinner with John and a few other colleagues, and one of the people, I think it was Jessica, asked. We started talking about machine learning and artificial intelligence. And she asked me a question. She said, what do you think the area where machine learning and artificial intelligence will have the biggest impact? And I didn't even think about this and immediately answered healthcare. That's what really is the biggest impact of these technologies that are growing more and more. And as you will see, not without controversy, not without constraints. So today, we really wanted to share with you a little bit of making sure that at least we understand the foundation of what this is, what is not, but also what are the applications, and more importantly, what are some of the constraints and some of the debates that are taking place regarding this. And I don't think it's working. Yeah. It's teamwork. And the teamwork is really good, because even when we go to the questions and answers, I answer the easy one, Balaji will answer the difficult one. And I'm really here to assist him more than anything else. So this is what we will share with you today. We'll start with a little bit of context. Then we talk about the foundation of machine learning and artificial intelligence. And let me tell you, machine learning is very personal to me. It goes back to the time when I was born. When my mother was pregnant, my parents were talking, what should we name our new son? And at that time, a little bit more than 50 years ago, they knew that one day I will be presenting to a group of distinguished doctors. So they wanted my initial to match machine learning. They named me Moez, assuming that the last name is Limayem. So that's the ML the story. It goes back 50 years ago. Yes. And of course, artificial intelligence. So we'll talk about a little bit the foundations. We'll talk about areas of opportunities for both in healthcare. Also, we really want this to be very interactive. So Jennifer, thank you for your help in setting this up, and even our colleagues online. If you have questions, raise your hand or write it in chat, and Jennifer will let us know. And for good questions, always there is a free sandwich for that. And also we will end with some of the human and system perspectives and how professional healthcare can interact with these technologies and vice versa. So let's talk a little bit about the context. If you talk about an industry or a sector that is under considerable amount of scrutiny, regulation, change from different forces, the first thing that comes to your mind is healthcare. This is the area really where yesterday is very different from today, and we know today is very different from tomorrow. I would say, unfortunately, when we compare our healthcare system here in the US, it is very inefficient compared to many other healthcare systems in the world. I don't know if you've heard about the State of the Region. It's a project that we work on, the Agentbased with the Tampa Bay Partnership, and we compare our region, Tampa Bay, to many other, 19 other regions, Dallas, Austin, Minneapolis, St. Paul, and Miami regions on different key performance indicators. And we saw, for example, in healthcare, that if you take Tampa Bay, 1 out of 8 people are uninsured. The national average is 1 out of 10. If you look at Houston, one of our benchmark, 1 out of 20. If we compare the cost of healthcare in the Tampa Bay region, we're unfortunately bottom. We always say thanks God for Miami, because it's really we'll not be funding this. Sorry for people from Miami. The change. Just trivia question, and I'm sure you know this. We always talk, and I know my friend Dr. Charlie Lockwood always mention this, about the progress in the number or the change in the number of knowledge and in healthcare and medicine. How long did it take the knowledge in medicine to double in 1950?
50 years.
50 years. 2020, how long?
5 years. 5?
No, less, 0.2 years, 0.2 years. And now we're even talking about even less. So it's incredible, the change, the rate of change. So this is where today we're going to try to see how healthcare providers, physicians, and all professionals and administrators, how can we leverage on these technologies so that not only we understand it, but we shape it. And I'm so happy you're here today because I really think you are, as John mentioned so well, this is part of the future. And the best way we always to predict the future is to help make it. So hopefully you will have enough knowledge today to do that. And of course, we will talk about other broader social issues related to machine learning, artificial intelligence. Now, we're going to go to the first concept with Balaji on machine learning. Balaji, what is yours?
Thank you, Moez. So I didn't know about the ML, Moez, Limayem.
Oh, yeah.
First time I heard this, so I'm not sure which ML is more transformational.
Yeah, machine learning for sure.
Tough one. So, but so what we'll do in the first part is I'll go over machine learning and in AI and highlight a few issues which are more conceptual. The goal here is, since we have a diverse group of people who are experts in science, your knowledge of this field may be high or low, right? So we're not assuming that, but we want to make sure everyone is somewhat at a level where you appreciate both the power as well as understand some important limitations and how to manage it, right? No different than other types of technology. So machine learning itself, and I try to separate machine learning and AI. Sometimes they are clubbed together, and we can talk about why that is the case. We'll start with machine learning first. Machine learning itself is a field that came out of primarily computer science. The focus was on learning from data. The idea is, if you have a lot of data, can you generalize from this data? Sorry? I thought there was a...
That was a noise.
Okay. Yeah, so if you have a lot of data, can you learn from it? Can you generalize from it? If you see examples, can you pick up something and then learn the broader concept? That was machine learning. And in practice, this became very synonymous with learning predictive models, given large amounts of data. And so the kinds of models in the machine learning field are variations of what many of you may have seen in statistics courses. Right? So I'm assuming a lot of you at some point may have done your stats courses and if you remember some of those. So these models are more, they're similar in a sense because they're also building a model from data. They're different in the sense that they try to innovate in terms of representations, right? Learning things like a tree from data as opposed to an equation. And so a lot of work in machine learning focused on developing different types of representations of what a model could be, and then building methods to learn these models from data. Right? And that was an example of one model, and there are hundreds of different machine learning models. The one that is most popular these days are deep learning models, which are artificial neural nets, but very deep. And this was motivated by human neural networks originally, a few decades ago. And that research has become exponentially more successful in the last few years because of computing power, data, and being able to design and learn massive artificial neural networks that learn from data. Now, in this example, you can see, for instance, the input is an image, and the output is what that image is, right? So this is a machine learning model that excels in problems like image prediction and image classification. But at some level, this and this are similar, right? They're similar because they're both trying to learn different models from data. They're making different assumptions as to what is the representation of the model. Right? Is the underlying model within your data, is it a decision tree model? Is it a neural net? Right? And the answer often is you don't know, right? Because what you're trying to play the guessing game. Right? In most machine learning scenarios, you're given large amounts of data and you want to learn the correct model. Now, if you knew what was the correct model that was generating the data, right? So we sometimes call this God, right? So God created the data. So if you knock on God's door and say, how did you create the data? And God says, oh, I used a neural net. Then if you build neural net models from data, you'll do really well, right? In practice, we don't have God, right? We have data. So we try to build different types of models and then test them on data to see which is likely to be a better approximation. And so these types of models offer massive amounts of flexibility in building, learning very complex representations. And they've been phenomenally popular, effective in so many different use cases. Now I want to touch on a few important concepts so that you understand the heart of some of the issues here. We talked about God, right? Saying if God was generating data with a hidden model, what would that be? I think I just destroyed your pointer here.
But Balaji gets really excited when he talks about it.
And so in the machine learning literature, this is called data generating process. Right? So if you know the data generating process, then you can pick a model that is close to the data generating process. Right? But whenever you work with data, before you do anything, before you build any machine learning model, as a scientist, the first question to ask is what could be the data generating process that is generating the data that we're seeing? The answer to that will almost always guide you into picking good models. Right? Because if you don't think about how the data was generated, right, you're not engaging in perhaps the most fun aspect of machine learning. And a lot of people don't do that, right? They think machine learning is magic, and magic will learn stuff from data, right? And that never works in practice. Now, there's a lot of interest in symbolic versus connectionist representations in machine learning. The symbolic models are the tree. An example was the tree you saw. A connectionist model was a neural net, artificial neural net. These are fundamentally different representations, and they have different trade-offs. Right? The symbolic models are easier to explain when you learn them from data. And so in medicine, and so many examples, you don't just want to learn from data, you want to be able to explain what you learn. Symbolic models are good for that. The artificial neural net models are very powerful, and they can work with very different types of data, but they lack the transparency. Right? When you build it, you can use it to predict, but it's very hard to look in and say, what is it doing? Right? And so that's the trade-off we often face. Evaluation in machine learning is extremely important, primarily because in simpler statistical models, you have data, you can fit it, right? But in simpler statistical models, if you have data, the chance of overfitting the data are quite low, right? Because the number of parameters you're estimating in a statistical model is limited. In a machine learning model, particularly the neural net models, it is common to estimate hundreds of thousands of parameters to estimate that model. Right? Now imagine the power of picking 100,000 different numbers, right? And you can pick 100,000 different numbers so that your model matches your data perfectly, right? But it might end up learning everything which is there, some of which is real and some is just noise, right? And then when you use that model in real life to make new predictions, chances are you'll see bad performance, right? And so these are very complex tools. And the best way to use it and the best way to build it is to focus on evaluation, right? So to make sure that when it's being built, it's being tested on out of sample data, new data coming in the future in order to see how well the model is doing and to understand whether we have overfit it, right? We've used a really complex method in a manner which went beyond just learning from the data itself. So I'll skip this a bit, but there's a very important notion of model complexity. here. Machine learning models, you can build very complex models and very simple models. The trade-off is that complex models give you the power to learn very complex relationships that are there in the data, but they also come with the risk of overfitting, right? So this is a scenario where you simply cannot have your cake and eat it too, right? So you have to make the trade-off in practice. And so sometimes simpler models are better, right? Because they don't have that risk. But if your underlying data generating process is complex, you lose the ability to learn. So this is where intuition plays a role. This is where domain knowledge and people like yourself, when you know your problem and you know your data generating process, you can make very good choices on what model complexity might be optimal for the kinds of problems you face. We are also seeing in machine learning that the world keeps changing constantly. Right? And the idea here is that this is called concept drift, that the underlying phenomena that you're learning is not static. Right? It keeps changing, and the new data reflects some change that has happened in the underlying world. So knowing this is important because you have to be able to ask yourself, in what scenario is change more common? And if so, in those scenarios, machine learning models have to be retrained appropriately in order to make sure that it is capturing what you want it to. This is probably one of the most important confusions that people have. And in medicine, this is extremely critical to understand the distinction between these two things, causality versus predictability. Machine learning models excel at prediction. Right? If you have large amounts of data, you can build great machine learning models to make amazing predictions. Right? That we know. These models are not here to bring out causal findings. Right? This is not the intent of most machine learning models. There is a sub area now called causal ML, which is getting a lot of attention, but this is not the focus of these methods. Now, the most common mistake that people do is they use machine learning methods to learn a model. They look at the model and they start interpreting it as if they found causal relationships. Right? This is the most common mistake to make, and even experts make it. Right? You build a decision tree from data, you see that it's purely based on some procedure that was given to a patient, and then you start interpreting that as, look, this procedure caused this outcome. Right? The answer is absolutely not. Knowing that someone had a procedure is useful to predict the outcome. But these models, there could be a million other things behind the scenes that are actually causal that have nothing to do with the procedure. And so these models exploit correlations very well to make predictions. Right? And as everybody here knows, the world of difference between correlations and causation. So that's a word of caution, but there are newer methods coming up. Right? So again, in your head, you have to be clear, going into a problem in healthcare, is your goal causation? Do you want to uncover causal relationships, or do you want to predict? Right? And the answer to that will change how you approach your analysis as well. One of the things that we are starting to learn a lot in the last few years is that these models are also not geared to be fair. They're geared to learn what is there in the data. And if what is there in the data was the result of practices that were not fair, these models will learn to be biased, right? Because they're learning from the data that you give it. And there was a recent few different articles in medicine too that had shown this out. I think there was one that showed that African American patients were not provided the same options that other patients were, adjusted for risk scores. Because predictive models that were being used in healthcare were recommending treatment paths. And there was one that was built by Optum Health that was used by a lot of hospitals. And subsequently, researchers who analyzed that were able to show that those models were biased. They were simply not recommending certain treatment paths for African Americans adjusted for the risk score. And this caused a big stir in medicine, and there were obviously questions raised. This was published in Science a couple of years ago. And these types of articles are going to start coming, because now at least we know to look for this issue. Right? Earlier we were not looking for this. Now we know that this is an issue, and we have to at least start asking, how do we find it? Related to this is just unexpected consequences. Right? So lack of fairness is one example of an unexpected consequence. When you deploy these models in practice, it might change behavior in certain ways, and it's important to proactively think about what types of unexpected consequences one might have. Right? So these are all very fundamental issues, but they are coming up to the forefront in the last few years. It takes a while for these things to fully sink in and to make you a good practitioner, right, at some point. Most of you will end up working with people who do machine learning for you, but it's important for you to understand these so that you can ask the right questions to your research scientists who might work with you in this. So I just pause briefly there. Any questions related to any of that?
So if we don't know what the model is being based off, then who takes the liability for that? Like the person who made the models, the system itself, or the doctor who is using it?
So this is an excellent question. Again, I would think we are not experts yet in there. From what I have seen, this is a question that people are trying to answer now. Right now, a few years back, if this happened and somebody pointed this out, I would assume that hospitals and doctors can take their hand and say, look, we really didn't know, and that would be accepted. Today, if it happens, right, people are going to say, we've known this for the last 5 years. What have you been doing to proactively address this? And if the answer is nothing, that's a problem, right? So hospitals using ML systems should have something in place that is at least looking for things. Things can still go wrong, right? But if you show good faith effort at trying to check for these, I would suspect that legal liability and so on will be significantly lesser than cases where people. Now you imagine, it's a two-sided thing, right? If it's really good and you're not using it too, somebody can come back and say, hey, why are you not using machine learning when these other places are using and they're seeing better patient outcomes? My outcomes suffered because you ignored a very popular, very effective tool. So I think there's the right way to do it is to use it, but to ask these questions and to build a process around that's checking for it. The legal liability, I think, will slowly be figured out, and I don't know.
You're absolutely right, and this is a great question. I think it's a perfect case how technology is going much faster than the laws and policies in place, who are absolutely lagging behind. So I think Balaji absolutely hit the nail on the head. Now, what do we do in this case? This is why you're here. At least know the right questions to ask. And now there is an even new field where we can train experts to do the audit and the diagnosis of these models to make sure that they don't have inherent biases in them that could make the recommendations flawed.
Balaji, one of the things I learned in the course was the access to data and the accuracy of data. So you say data as if it's a commodity and you can go out and get some. The reality is some's good and some's garbage. And if you put garbage into your model, it's going to gum up the works and you're going to come up with a model that's completely ridiculous. So how do you overcome that when you've got these huge amounts of data? I mean, you can't go individually and check it or something. So how do you deal with that? The validity of the data, I guess. How do you address that problem?
I think you have to do two things. You have to keep questioning the data, right? And right from the beginning, you have to spend time understanding the data generating process before actually doing anything, right? And so people have started doing that. They've started paying attention to data quality because this garbage in, garbage out has become quite now well known. Second thing I would say, which is a more practical thing that you should do, is focus a lot on constant evaluation. Testing to see, is it correct? Is it predicting right? When new data comes in, we're making the predictions, we see the right answer. So suppose you have bad data in, but when you're testing for evaluation, it's doing really well. You got lucky. Yes, your data was bad, but you're performing really well. You're able to predict well. So chances are maybe the good outweighed the bad in the data enough so that the model didn't get confused by the bad data too much, right? But if you keep testing and you realize the model is not performing, then you may have to go back and say, look, it may have been poor data. So let me go back and think about, is my data right? So I would say two perspectives. You keep looking at your data, make sure that you can ask all the right questions to trust quality. At the same time, keep doing evaluation, keep testing it as it's being deployed, so that you will know when it starts performing poorly, and that could be a sign of poor data.
And always the way to prove that the data is valid and the process, right, the rigorous processes were put in place to not only collect the data, but also clean the data and have that process nailed down, is on the people who developed these systems. But as users, we need to ask these questions, and they have to convince you. If they don't convince you, I would have some really strong doubts. And this is why the course that we had, or even workshops like these, are so important, because we will never be experts in data cleaning and data collection, but at least hopefully we'll know what are the right questions to ask and see if they can convince us that actually the data, the way they collected the data, the way they update the data, they clean the data, are rigorous and valid.
I've heard from some others that the analogy is a lot like electronic medical records when they were being pushed in 2000 and 2005, where everybody wanted to push an electronic medical record and come through before the Epic and Cerner. It was a matter of, you can't just accept it. You have to do what you guys are saying, ask the questions, validate.
Validate, and that's the bottom line, right? So as long as you're validating, you're in good shape. Most of the time, people end up just blindly using without thinking that they should be validating. And I think that's the best practice.
Dr. Mohapatra has a question.
Yes, go ahead, Dr. Mohapatra.
Yeah, so I was thinking about the curation. In the process of cleaning the data, you're actually trying to curate the data. And the question is whether the individual biases there also can play a role, and the limited knowledge can also be affecting the process. So how do you know that the curation has done good enough job to come to the right model?
That is an excellent point as well, because we talk about the knowledge that humans can bring in. Many times that comes in the form of identifying what data you want to feed into these models and so on. But the same thing which can be a plus can also be a minus. So if you end up taking things out and it reflects more of your bias than a positive action, obviously that's not good. So I would say number one, knowing to ask that question is itself a great start. Right? Again, many years back, people were not even asking this question. Right? So this is a fantastic question to say, when I'm working with data, am I introducing bias? If so, how? Right? And many times just asking the question and thinking through this results in good practices. The second thing is we go back to this issue of knowing how to test your models. Be very clear how to validate models and make sure your models are being validated extensively. So that mitigates the risk that may come from bias, right? So if you bring in your bias, you should not expect the model to perform as well. In cases that can reflect, right? So you might want it to do well for all racial groups and so on. And now that you're testing it there, you can see whether it's not. And then you can go back and say, maybe something that I did caused this problem. So yeah, I think it goes back to the same thing, right? Validate, test on a constant basis. This finds a lot of problems. But also how you test is important, right? Not just testing for accuracy, but testing for a lot of things, right? Accuracy is one thing you want to test. You also want to test for equity, right? If you're using these models in a clinical setting, how accurate are the predictions? You want to make sure it's same as what it was or better. But you also want to track this by issues like race and by groups like race and gender to at least think why, if it is not predicting the same, at least why, right? And so when we track it for performance and for equity, a lot of these problems go away. At least we find them early, right? So great question. So briefly wanted to, the one machine learning perspective was learning from data. And another machine learning perspective focuses on the learning. And this is a lot of these are new ideas that are coming out. And the question that is being asked, here is that humans learn very differently. How can we make machines learn like humans do? Right? So for instance, when you learn how to drive a car, on a road next to a cliff, you don't need to fall off the cliff many times, right, to make sure you stay on the road. Right? But a lot of machine learning algorithms that use these methods for reinforcement learning, they learn by trial and error, and they need to fall off the cliff many times. In real life, humans don't need that. Right? You look at one patient who has a certain unique behavior, humans are able to quickly learn something much broader from that one patient encounter. A machine needs thousands of data points that reflect the same thing over and over again before it can learn it. And so the question that's being asked now is, are there machine learning methods that can learn with limited data? And there are new ideas called few-shot learning, zero-shot learning that are coming out that are trying to do this, including reinforcement learning as well. So reinforcement learning is a learning by doing type of methodology in a system. The biggest success was Google had trained a reinforcement learning algorithm to learn how to play the game Go. And it beat the world champion in Go in, like, I think 3 weeks. Like 3 weeks before it knew nothing about the game. 3 weeks later, it got so good that it beat the best human player in the world. Right? And it was just a remarkable achievement. And so now these types of things are being tried. So in medicine, for example, I'll show you one paper recently that attempted to use reinforcement learning to figure out how to take somebody off a mechanical ventilator at the right time. Like, what's the optimal point to take somebody off a ventilator? And instead of having humans do it through set rules, this paper showed that if you can build a reinforcement learning method, the reinforcement learning method can figure out when to do that better. Right? And so these are interesting ideas that are coming. Transfer learning is a very novel idea that's coming out as well. And so humans do that well. You learn in one context and you go to another context and you're able to transfer that knowledge over. Right? So you've learned in one disease type, now a new disease comes. Very quickly you're able to use some of your knowledge from one group to this other group without needing lots of extra data. So now in machine learning, similar ideas are being tried. So there are some entities that have millions of radiology images with tumor labels. Now an individual hospital may not have. An individual hospital may only have a few thousand. Right? And so some of these methods need millions of data to train. So how can you train a model if you only have 1,000 images to label? The answer is there are methods of transfer learning. So the idea in transfer learning is somebody else has built a model based on 1 million images. You take that and you add your 1,000 images and you tweak it. Right? So now you get the best of both worlds. You get the best of a model that a group built, and then you're able to add your own data so that it customizes to, in a sense, to your patient group and so on. So these ideas are very powerful. This is a too complex slide. The only thing that I'll point out here is that there's a very simple lesson here. The gray box is a machine learning method and lots of details beyond settings and parameters. The boxes outside are everything around it. Right? And so what we are also starting to understand is that success or failure of machine learning, the way to think about it is not models, but systems. Systems are not just the model itself, but what the humans around do with the model. How do they act on it in practice? What rules do we put in place? And so it makes sense to think of designing better systems, not better models. Right? So you could have a fantastic machine learning model that predicts hospital readmission for a patient who's being discharged. But how would you act on it? Right? So if a hospital puts together a process to act on that signal, and the process is not perfect, or the process is just flawed, the entire system might fail. 6 months into it, you might figure out that the readmission rate hasn't changed. Right? And then you go back and say, fire the data scientist who built this model. I asked this in my class, saying, should the data scientist be fired? Half the students say, yes, half they not. Because the challenge is, where do you point the blame? Right? Is it a poor process or is it? So now, rather than thinking about blame, you should think about this as a design idea. Right? When we use ML in medicine, what's the entire system that we are building, not just the model? And how should we evaluate the entire system? Right? Which is all the processes around it too. And if you do that well, better chance you get better outcomes. Right? So that's the notion behind ML in complex systems, which is to say that you have to model the rest of the environment as well. And how do you model that before you build these things? And there are ways to do that using agent-based simulations, for instance. It's a very popular methodology to model the rest of the environment. Right? So you have a machine learning model. Now you want to model the real world. You want to model patients, doctors, other hospitals, what happens. You can design and run large simulations that actually do dry runs of those. So AI itself, has a separate history, and they are converging in a sense. The motivation for AI was always, how do you build machines that demonstrate intelligence, right? Now, intelligence was always the focus of AI. Right? And so initially, intelligence, so the kinds of use cases that AI works with are just how you demonstrate, how you build things that make it look like human intelligence. One of the earliest examples was the chatbot. So if you can talk to a person, humans are good at talking to people. So if you can make machines talk to people, that's AI. And how do we do that? So we had a chatbot about 40 years back that did things like this, right? That automate, that used to talk to a person. Today we have the same thing. We have Google Home, Alexa, and others, which are also chatbots, which are also talking to people, right? Siri, most of you use these things. So many years back, in the context of demonstrating intelligence, one of the earliest efforts in medicine was the system called Mycin. So Mycin was, quote unquote, an AI system 20 years back that had a whole set of expert rules that came from textbooks in a box. And then the box used to make diagnosis based on these rules being satisfied in the data. Now today too, you have that, right? So you have AI systems that are fed massive volumes of patient data, and they're making predictions. This was a competition in China where this was, I think, 4 years ago, where they actually ran a human versus AI competition where they had their radiologists, about 25 or 30 of them, and they were showing them images. And they had to basically say whether this was evidence of a tumor, if so, where and what kind. And when the radiologists were doing it, they had a trained AI system based on deep learning that was also doing the same thing. And in this competition, basically, they showed that the AI system essentially beat their best doctors, both in accuracy as well as speed, right? And this was a very important moment because now it starts showing the power of these things, right? If you're given the right data, but it also creates questions of, now this doesn't mean that the humans are no longer necessary, right? But it raises the question as, if you had this technology, what should the humans be doing? Right? How should a radiologist be doing their work, or a team slightly different, where this is their tool now, right? It's not something that is competing with them, but this is part of their toolkit. How can they learn to use this so that they build, better systems, right? And that's
and Balaji, I think this competition was biased because it did not include USF health doctors. The results would have been different.
That's a great point. I definitely agree.
Yeah, change the slide.
So I think, if you look at the chatbot in the medical diagnosis case, over 30 years, AI has looked at similar problems, trying to build intelligent systems. But what has changed this in AI was that 20 years back, that intelligence from pre-programmed logic that humans put into the AI box. Today, that's not happening. Today, what we put in massive volumes of data. And we try to learn these machine learning models that then use the data to do things that's where the intelligence comes in, right? And so what we're doing today is scalable, right? As new data comes in, you can keep feeding it, the system keeps getting better, and it adapts with new data. So the power that we have today to do things like this is just massive. So within AI itself, to somewhat demystify it, you can break it into, there are 4 components today that are available, I want to say almost off the shelf, meaning you can go and purchase it with software vendors, hardware vendors, and then put it together to create magic, right? So AI is not magic, it's just carefully constructed design of a solution. The 4 components that are usually common in AI systems are, in many cases, there's a hardware and robotics component, right? Not all, but this is like in self-driving cars, right? You need hardware that can do things like this. Now, data and machine learning and methods to do that is a very important part of AI. Right? And so you do need all these algorithms that can generate these types of models. Then there are 2 other components that are quite commonly used that will fall broadly under visual perception and speech and language understanding. for which again, there are tools off the market. The visual perception would just be image recognition, right, in radiology. It could also be actually being able to see, right, through processing video and doing things based on that. So there are methods and algorithms that can provide you with that capability, right, and you can use it to design whatever it is you want to design. And same thing with speech. Now there are lots of technologies that can that can even talk to you directly that are being used in systems. So when you start piecing this together, you can create solutions that say, if I want to diagnose diseases from images, then we need a combination of tools that can do visual perception with machine learning pieced together. Right now, there are many examples in many places that are trying to detect potential stroke and other emergencies in real time, right? So these things might look at voice patterns of a patient, right, and track it constantly. And if your voice patterns change, coupled with some other biometric data that's coming out of you, it might be an early indicator of something like a stroke. And you can, have systems in place that process this. So these things are, particularly voice is being used a lot in healthcare now in many lab settings. Where people actually have data and they're trying to see how can I use this to predict patient outcomes. I think Dr. Sinod mentioned that when someone even clears their throat, sometimes it might be a sign of infection being higher than normal. And if you have a system that can even detect that, things like a throat being cleared, these are early signs that can be picked up by systems today. So again, today's AI is a mix of all of these things. You have machine learning methods, you have robotics hardware. There's a big importance for domain knowledge, right? It's very critical in how you formulate this. Design thinking, creativity is important because you have to approach what you're doing from a completely different perspective in order to build successful AI systems. And patience and willingness to fail. A lot of AI systems fail before one succeeds. And you often only hear about the success stories, but you don't hear about the failures. But failures are part of the game. Right? They just don't get publicized as often. Now, as I had mentioned earlier, in healthcare, there's a ton of work. If you look at your medical journals now, in all the top fields, you start seeing papers in ML and AI showing up in some of the top medical journals. And there are many, many, many different use cases, different problems that are successfully being used. At the same time, one of the biggest failures in medicine was, unfortunately, IBM Watson. And many years back, MD Anderson Cancer Center spent about $75 million trying to get this to work. And finally, they said, this is not working. And they got rid of it. It was a very expensive failure, highly publicized, could have been avoided if they didn't approach AI as magic. If they had approached AI as something that they had to learn so that they use it the right way, this could have been avoided. Right? So they just went in thinking that this is magic. We are buying magic. It's going to solve the problem of cancer. And much later, they realized that it's not magic. Right? We know how it works, and it's simply not giving us what we thought it would give us. So, but IBM and others have learned from this, and so they don't oversell now. And not just IBM, thankfully, other vendors also have learned from this. And they are much more cautious when they are pitching products now in terms of what it can do and what it cannot do, so that you can use it properly. So lots of exciting things happening here. So this is there are many new ideas in this slide. Each of this we can spend hours talking about. And I think we touched upon a lot of these things in our work. The one thing I don't think I mentioned much here, there are two things we'll wrap up with, the network mining and augmented intelligence. There's a lot of interest in representing patients as graphs and doing things differently on graph data. So Epic and other data sitting in these health platforms are being processed as either text and numbers, but there's a slow movement to trying to represent them as graphs, as networks, and then to learn interesting patterns from graphs. There are probably 10 or 12 papers in medicine that have started doing this, but in future, you will find interesting technologies that can go into Epic and construct interesting graphs from there, where you can see patients, procedures, and things linked in a very visual way that will quickly summarize what's going on in your data. And there are many other things here we can do. I wanted to, have some time to just think about, from your perspective itself, how ML and AI can be used and how it can be combined. But maybe we'll end with this. I'll briefly touch upon the human perspective. Combining people with machines and doing this important is going to be really the most critical thing, right? Because you have experts in your field, you have these technologies now that can help you. Your job is, how do you combine? How do you design this? We know how not to do this, right? So this was unfortunately a really sad graph where the blue arrow was the decision by a human, the yellow was a decision by a machine, and they kept going in opposite directions. So this was the Lion Air crash, right? So the machine AI kept pushing the nose down, the pilot kept lifting it up. So this happened for about 2 minutes, and then the plane won, right? The machine won in this particular case. And this was really, we're starting to see these types of scenarios in extreme cases, right? Where the AI decision and the human decision were not in sync. And at some point, one, quote unquote, won, but ended up with like very bad outcomes. Now, at the same time, you will have a million examples which we cannot show, where the pilot may have done something wrong, but AI may have averted that, right? Because those scenarios we don't even observe, right? And there are so many planes flying all the time that are controlled by these systems, and we don't even track these types of, we don't know that a mistake was made because it was corrected. So that's, it's just that it's important to think about how to design systems that combine the best. And the answer is, it's not easy to do. Right? So you want to try to start that process of building augmented intelligence systems and what that means for you. So we'll stop here, and mainly with the questions, if possible, based on this, where you think you can use this in your own practice. Now, I think Dr. Moez was also telling you about, we have our machine learning certificate course, and I think the next version kicks off in May. It's a 6-month course where we meet once a month for 3 hours. And you actually get deeper into the methods, you build algorithms, and we have PhD students who help you with projects there. So if any of you are interested in doing that, please reach out to us. We start in about a month. So questions or thoughts on how you could use?
Yeah, I have a thing that's always, with the deep learning bothered me, in that as far as I know, medicine is full of bias. And an example might be that oximeters which measure the oxygen in the blood are calibrated for oxygen. So really 1/3 of that data you could get from it's totally flawed. Even if you look at Fitbit, again, not calibrated for people of color. So you get erroneous readings. I don't know, the bias to me, and whether it's experiential bias or what, really flaws a lot of medical records that people are using to make decisions about. I think a doctor, to be trite, tends to see what they know. So an allergist sees somebody with wheezes, they have asthma. A pulmonologist sees them, they might have something else.
I think your question is a really good one, John, and that's why I like a lot this concept of augmented intelligence and not artificial intelligence. This is to help, not to replace. And hopefully when you know the foundation, you will ask the right questions. And as Balaji mentioned, you do your own validation and testing to detect these biases. And I think there's a lot of progress that is made. And I mentioned a new specialty now to audit these machine learning model. But the one thing I think related to this that I really want to think about, think of a couple of decades ago, or even a little bit more, travel agent. We had travel agent everywhere. We couldn't, if you want to fly somewhere, you go to a travel agent and you buy a ticket. Travel agent is a profession that has completely either disappeared or completely changed. Now they're more of advisors. They help you plan your vacation or your trip rather than just go and book a flight for you, because we all go and book our flight. I really think the healthcare providers, the MD's job is changing. It really is changing from just applying what we learn in medical school to treat patients, to knowing how to use these tools in the most effective and efficient way. I can tell you, these tools will never and ever replace medical education. But I think it is and I'm really hoping that eventually this will be incorporated in the curriculum of medical schools, because this is the future, that your jobs will be changing and is in the process of changing. So understanding the limitations and the pluses and minuses of these tools is just crucial, really is crucial. That will make the difference between a good doctor and not as good of a doctor.
I think your point's a fantastic one in a different way as well, because this could be a great research stream for somebody in medicine, right? Where there are probably so many things that have been calibrated in a way which was not equitable.
Yes.
And so I think you can just imagine building out an entire research stream just on that and tackling one problem at a time to fix it.
Yeah.
Things like that, I would imagine, would be easily funded by places like NIH and NSF, because now the problem of equity is up and people have seen biases, right? So now we're looking for solutions, and teams that can start systematically going after that, I think would be awesome. And I think Dr. Mike Lozano had also pointed out something really interesting here, which is that you can also formulate machine learning problems itself to detect bias. That itself becomes the machine learning task. And there are methods like GANs, the generative adversarial networks, that are starting to get used in order to show that you can create data with bias in it, and therefore you can test if the data has bias in it. So GANs are another really hot topic within the ML area and can be used to also detect bias. Excellent. Thank you. And so I think Dr. Shyam was talking about regulatory issues in applying this. So this is definitely going to be, there are lots of discussions that are coming up here, and the role of unanticipated consequences as well as transparency and explainability are becoming important. And I think regulation is slow because of what Dr. Moez was saying, which is that regulation is so far behind technology. And but these discussions are starting.
There was a case, sorry, it is related to this. Earlier on, when we started having expert systems, the first application of artificial intelligence, and one used by one doctor. Unfortunately, the patient died. The sequence of event was really interesting. The family of the patient sued the doctor. The doctor sued the company who made the expert system. The company who made the expert system sued the expert who gave the logic behind the expert system. So imagine you're a judge and trying to sort out all of these. At the end, the judge ruled that the doctor is responsible at the end. But this is a good case where the liability issues and the laws are really lagging behind the technology.
Yes,
sorry, yes.
That's okay. I was just going to say, to that point, and to the liability question that we asked earlier, I mean, we have recommendations that are evidence-based guidelines, they're guidelines. And we go away from those guidelines often depending on the case. And ultimately, it is kind of the physician making those calls. But I do agree that obviously the liability needs to be maybe put off so that we are more daring, to veer from the ACC guideline on whatever we're deciding on. But I also want to say, having completed that course, and Balaji, I'm so glad you're here. I'm really happy that you guys came. It's interesting. Like my question is, where is USF going to be in 5 years from now on these topics? These conversations are starting now, but we're years behind the Stanfords and the Bostons of the world with kind of integrating the AI plus the medicine. But we have the health system for it. And I'm just kind of asking, having all you guys in this room, what's next? What are we doing about this?
Yeah, I think the certificate is a good start. As I just mentioned, my dream is that we incorporate this in the curriculum, really in the curriculum.
I think so too. There's a board certification in clinical informatics, which I'm applying for, having completed the course. I don't know if I'll qualify because I'm not like a CMIO of a big.
This is the last year you can take it without fellowship.
They actually extended it, Joe.
Yeah.
So they extended it to 2025 without.
Oh, they did?
Yeah, they extended it to 25 because of COVID.
Gotcha.
So I'm applying, and then you sit for this board exam, and you have these new letters behind your name. But then what? What am I going to do with it?
Yeah, exactly.
In my department, how are we what's coming next? So I'm just thinking out loud.
Yeah, and you're right. I think USF, what distinguishes USF from other universities are the silos are really down. When you think about it, we always have some sort of silos, but it's incredible the work that we do with USF Health and with TGH. We started this Institute for People Development where we train everyone at TGH. We do a lot of curriculum with the College of Pharmacy. We do it with also the College of Medicine. So all the stars are aligned to go to the next level. I totally agree.
I think you have to really try to also build a small group here.
Yeah.
Because at Moffitt, last few years, they built this machine learning group.
Oh, yeah.
And I know Dr. Isan Naka,
Yeah.
Karim, you met him too,
Yeah.
as part of our certificate program. So he leads that group. They've been hiring people, they have initiatives in place, and they're trying to reach out to the Moffitt doctors to then now start bringing problems, and then the machine learning group tries to then build solutions. But you probably need to think about the value of creating such a group here. And will it be faculty? Will it be research scientists? Will it be PhDs? Will it be postdocs? Will it be working with people like us in different colleges?
Yeah.
Maybe some combination, right?
This is so interdisciplinary, and USF is well positioned.
I think the way to do it is the way implementation science has gone, where talking to some of the great researchers we have here, like Risa Richardson, they're really looking to bring in executive stakeholders, because the whole goal is, it usually takes 15 to 17 years for your goal of implementation study research to hit actuality. And so part of trying to overcome that is make the research more interdisciplinary, including using executive stakeholders to be involved in the research and pushing them more to be part of the design rather than be part of the vetting and validating at the backside.
Part of that entire cycle.
Right.
I can tell you as a physician scientist, we used this when we were doing translational research. I did like what you said, Dean, where it's augmented.
Yeah, it really is.
I think that when we're talking about AI, and we're talking, we're not talking about Star Wars, and we're not talking about the medical bots and all that stuff. I jest, but it's true. But I would also point out to a nation like Cuba, where the technology is from the 50s, and they send physicians all over the world. They don't even use the technology, and they still do fantastic medicine. So it's this dichotomy of, well, we want to keep up and do cool stuff, but also retain that. This is what you gentlemen said at the beginning, Professor and Dean, that you have to maintain that, because if you lose it, you don't ask the right question, poof.
Yes.
If it's not in the algorithm, if it's not in the set, you're not going to.
But you have to be trained to ask the right
Precisely. And so does your macros.
I know you.
And similarly, like the training sets have to be very similar to the testing set of data. And at our VA, I work at the VA, where Dr. Lazama has been leading this AI project for many years. So we've had several AI projects with other VAs. Dr. Mohapatra has also been a leader in this with some of our studies as well. But where we see a problem is like we have to integrate it with our current system. We have CPRS, we'll go to Cerner or Epic, whatever. But when it gets integrated into that, that's when it actually makes a difference. But otherwise, just doing these tests, we have several studies that we are doing, and we go to our computer science colleagues, and they will test it, and they'll do additional things in addition to augmentation, like they say we flip it or we do other things, and then the accuracy increases, but it's of no use until we can actually implement it. VA is the best place to do data. We have golden with that the
Data warehouse.
Yes, it is so true, and this is exactly related to the slide that Balaji showed, where we're talking about a system, not just the technology, hardware, and software. So the processes, the humans, even the culture are really important of that ecosystem. And if you ignore that ecosystems, you fail.
So what collaborations do you offer? Like you have this program for 6 months, 3 months, 6 months.
Yes.
But what other?
I think that's a good start. So would you like, we have the admission letter for that certificate.
I'll find officer.
We can sign it. I think this is really good, but I like your question. I think it's time for us to the leadership of our college and the leadership of USF Health to have these discussions, to really try to see how we can, in terms of education, but also research. I think you're giving us homework. I thought the other way around.
I like what Kareem said. You make it longitudinal.
Yeah, you make it really longitudinal.
Longitudinal.
Yes, you make it longitudinal, and USF is well positioned for this, and we consider you great partners at the VA. You're part of the.
A very simple thing that I tell people is always start with the end in mind. Imagine that this has been done. Think of what system you would then be deploying that uses this to add value, right? And if you're not able to think of that system, then don't even waste your time trying to do the ML with 3 months to do accuracies, because now you don't know how you're going to use it, right? Now, if you start with the end in mind and you pretend that this job has been done and you're designing the entire solution, that's when you know what all has to also happen for this to truly add value.
Yeah.
And if that cannot happen, then maybe this is a bad project.
Normally, I would say the aviation system, but you showed that example, and that's.
But like I said, I do want to stress that there have been a lot more successes there
Yeah.
that you don't see.
You see the big failure.
Only see the big failure.
You've heard, you had Tesla there. You probably heard about the Tesla crash, where the Tesla system confused a blue track with the sky and crashed into the big track, thinking that it was the sky. So there are failures, and if you really don't understand this notion of augmented reality, but I really like your questions, and I think, Balaji, maybe we can at least start with a small group of interested scholars in this area. You know, the best is, as leaders, we can try to come up, but if it is also from the ground up, I think we can do so. Maybe we can think of combined, we can see also some colleagues from engineering, and just a small group.
IT too, because like you were saying, it's deployment.
Yeah.
You have to start thinking about how to
It makes
deploy
a
it
difference.
outside.
Yeah.
And so unless you have all those pieces together,
Yeah.
it's probably
So
not.
it has to be interdisciplinary, and maybe we can from there come up with some recommendations.
There's one more from chat.
And then after that, I think we got to break everybody.
So Mike, to attract like-minded physicians to collaborate. This is a great thing. I think we need some kind of a platform where people with this expertise and interest come together.
Yeah.
Now that could be, so that could be a
Huge
physical-
funding
could be a
opportunities.
social network type of a setting which is just for discussions around this topic. But this
We
is.
say that, AI is not going to replace physicians, but physicians who don't use AI might get replaced.
Yeah, exactly.
That's great.
That's a great.
That's great advice. And I
That's a
think
very
it's
good,
it's a great time to figure out how to combine.
Yeah.
And I think that's where the value is. And it's a very exciting place to be in. It's the best place to be in health, where the opportunities are very meaningful. It's being used a lot in marketing for the last 10 years, but a lot of